So this time, we have about 60% of the data available to us. We still have 4 sequencing runs out of 10 that are in Montreal that we don't have received. But we worked in an outside-in, so we basically compared controls to clinical first in order to see if we could find something. And we do have currently already 4.2 million sequences. Remember, the entire ELK study was 750,000. We're getting 2.8 million more, so we have about 10 times as much information as we ever had in the ELK. And because you compare everything to everything, it's a squared problem like a chessboard. It's 100 times as much data that we can actually filter in this case, okay? So what we can do is the all against all again. This time it's over 1 trillion word searches comparing things to each other. So if you try that on your Macintosh, you will probably use 1,000 years worth of compute time to do it. We have specialized hardware to do this with. Don't worry, we'll do it in a few months, okay? But we can also, because we have the cattle genome sequenced, map all the reads directly to the cattle genome and see if we find sort of hotspots at which things occur that only show up in infected animals. That's a much faster thing to do, and that's what we already have at hand, so we have some results from this. They are not patented yet, so I'm not going to give you any gene names yet, okay? I hope you forgive me for that, but shortly we'll write a paper and then you can read it and it will all be properly protected too. As I've said, it needs a lot of dedicated hardware. Our main assembly machine has a terabyte of memory. That's 100 DVDs worth of memory. Now, if you have your laptop in front of you, that has between 2 and 8 gigabyte, not terabyte, okay? So that's a specialized system. We have a CPU-intense system, which is full of FPGAs. That's the equivalent of over 20,000 CPUs. So you would have to use 20,000 Macintoshes to do that within 6 months. But we do have that sort of capacity available to us right now to do this work on time. What we have found is several hotspots which are all on a single chromosome. I won't give you which one, but I can assure you they are all related to each other. Now we come back to the question of this. Remember, I told you to remember in the ELK PLZF, it looks like that the same mechanism is working in BSE on the molecular level that we have seen in chronic wasting disease, and that's good news again, okay? Now, this one is not causing the brain destruction. This one facilitates the integration of endogenous retroviruses into the genome. So this thing has to be active when certain other things that really cause the destruction are also working at the same time. And this gene here that is behind it, which is also overrepresented, is actually facilitating the channeling of retrovirus genomes between cells. So these kind of mechanisms are sort of a side effect, but we also have the neurodegeneration genes at hand through the hotspot mapping that might be actually the cause of the brain destruction, not the infection. These things you carry around when you're born. These are in the egg, these are in the sperm, so they are not something that comes from the outside. This is not the cause of the infection. This is the cause of the end stage of BSE when things go really sideways and the brain gets destroyed, potentially. We have to do some other testing to verify that, of course. We are scientists, so we can't say this is it, but we say we have a very good lead now that we will follow up with some other experiments to actually verify. Again, the p-values for this are, you would have to do this time 10,000 times 4 million sequences in order to repeat that randomly. And I tell you, if PLZF shows up in the 2 of them, it's many more million times after that to really get that sort of a connection. So the plot thickens, that's for sure, and we are very keen on getting the other 40% from Montreal to get the study completed. So with only 60% of the data at hand, we can say there are CNA patterns indeed that are only occurring in BSE-infected animals. We don't have universal patterns yet, but the middle part where we would verify all of that is still out, okay? So we can't say that yet. The functions of these things have to do with neurodegeneration, and we have some of the same mechanisms that we observed in the elk that were 35 times overrepresented in the elk. Okay, these are not just any random things, again working in the BSE case. And most likely we can soon use a combination of a few of these patterns to think about a test. So what is then the new mode under which these two conflicting theories come together? We still don't know what the infectious agent is. But we do know probably that they trigger eventually retrovirus activity. These are things that come from your own genome. They are actually in all mammals, so these are very ancient genes. About 10% of our human genome is made up of these kind of sequences. So eventually, the retroviruses upregulate and downregulate a set of genes. We have found some of these that are being upregulated, so we assume that based on that, the genes that are controlled by these genes are actually then influenced as well. We get motifs based on this in the CNAs because cells are starting to signal there's something going wrong here, please do something about it. Unfortunately, the things that the body can do are not sufficient to keep you alive, so you still die regardless of the signaling, and we eventually get the destruction patterns in the brain that are being observed in the classical postmortem test. Is this something that is only in TSEs? Absolutely not. We find this in leukemia and liver disease, and we also find this in neurological disorders such as multiple sclerosis. So again, endogenous retroviruses are suspected in contributing to the progress of the disease. And these are speculations, but we are now getting to a point where we can design some experiments to verify that, okay, and see if that is really so or not. For example, we can take knockout mice that do not contain these genes, subject them to a BSE infection and see if they die later. So things like this are now in our grasp because we don't have to deal with 10% of the genome anymore. We have to deal with 3 hotspots in the genome. So that's a big, big difference. That is 3,000 genes versus 3 to study, okay? So what's the long-term plan? We will continue our study, identify the BSE-related unique patterns in the CNAs. We will see then if these are stable, so the genes involved in your genome, in the cow genome, are they actually identical in all of the different breeds so that we can make a test out of it. We then give that to someone else to verify, so we take our hands off and say, this is how it goes, do the same thing, and show us that you can repeat it. This is how science works. And then we work with a company that is probably right now working on paternity testing and such to make a test for this that actually goes down to $1 to $2 per head. So that's affordable. If you look into the SRM removal, that costs you $30 per head right now. So adding $1 or $2 to this is probably not going to be a no-go factor, okay? Now, how do we get this then rolled out? My suggestion, and I'm a 10-year full professor, so I can say anything I want. I'm not a government official, okay? I want the industry to adopt this as a voluntary measure immediately. And I tell you this because otherwise it's going to take 10 years minimum, and lots of resistance and lots of arguing and whatever, okay? So we have something similar where I come from in Germany, which is actually trichinosis in pigs. And if you go buy meat from pigs in the butchery, there's a blue stamp on it that says trichinosis free because this animal has been inspected by a vet. So why don't you make a stamp, I'd suggest greener, that's my favorite color, it says BSE free, okay? And you stamp all the meat that you have inspected with this technology with that, to use that as a marketing tool. Of course, we will still have to work with governments, especially of those countries that we export to get a formal acceptance, so the repetition of this experiment by others has to be done multiple times. And eventually, we can use this together with the cattle tracking, because if you do find a problem, you have to track it back to the source. So as marketing tools that allow us to actually get an advantage. And this thing doesn't just work for BSE, it works for other diseases too. Anything chronic, long-term, whatever it may be. So I suggest that we expand these testing tools to Johne's disease, mastitis, and you name it. Okay, whatever your problem is, if it is in that long-term range, we can probably look into finding markers for that with a similar approach. That's it. Thank you very much for listening to me. I know it's late in the day, you all want to go home, and I'd still like to thank the entire ALMA board for taking on that risk and funding this. As I tell you, it has been rejected a few times by people that don't believe that this is any good. And especially Ted Billier from the board, Bob Church, Rancher extraordinaire and good friend of mine, and Brett Fournier, who's actually my man-handler over at ALMA and who makes sure that we can really do the work that we are doing right now. Thank you very much.